Bismillahirrahmanirrahim. TCP Congestion Control is the final topic in our chapter. This is the third solution that we have developed in TCP for reliable delivery of information. An example is given here to demonstrate what do we mean by congestion in this case. We have a sender. In this case, we have a small capacity receiver. We have a small glass of water. However, so as you know, remember from flow control, we have to regulate the speed of water so that the glass does not get overflown with water. But even though the receiver is small, the network that we are using, the pipe, the transmission network that we are using is not congested. There's no congestion here, so we have no problem of the packets reaching the receiver. They reach the receiver without any problem. In this scenario, we have a sender and we have a large capacity receiver, okay? We have a large capacity receiver. We don't have a glass now, we have a bucket. But in this case, we have congestion here, okay? This part of the network cannot accept the same amount of, cannot process the same amount of water as the larger parts. So this part is causing a congestion. And as a result, if you see here, the pipe is not exactly free. We have water all the way up to the funnel there. Whereas in here, there's no congestion. The water is flowing freely, but in here, there is congestion. Something similar happens on the internet as well. On the internet, we can have two powerful senders and receiver, okay? They could both have large sending and receiving windows. The speed would be fine on both sides of the network. But in the middle, we have routers, okay? We have routers in the middle. These routers may not have the same amount of space reserved for their buffers, okay? Their buffers. So while the sender and receiver have negotiated the window size based on the sending and receiving window, these routers don't have the same size for their buffers. So there is a chance that when the sender sends the packets, they will cause the routers to flood. And this will cause packet loss, which will result in a lower throughput in the network. So we have the window at the sender, we have the window at the receiver, but these windows are actually smaller, okay? They have smaller windows. This is very much possible. So what does this mean? It means that the sending window, okay, at this sender is not based just on the receiving window for the receiver, but also based on how much can these intermediate devices accommodate, okay? So the window on the sender side will consider the minimum of the received window and the congestion window. Okay, so which one is minimum? It will consider that value. But how can we find out the window sizes? There's too many routers in here. That's going to be a problem. So instead, we have a mechanism called congestion control. Now let's see how congestion control works. So this is what it's explaining. We have router 1 and router 2 packets arriving, but router 3 cannot accommodate all these packets. There is congestion and it starts dropping the packets. So we have to avoid this situation. So the actual window size is the minimum of the received window and the congestion window. So congestion control occurs in TCP. How do we detect congestion in TCP? Number one, if there is a timeout with no acknowledgements, if there is a packet loss, we assume it is congestion. Remember, in this case, we are talking mainly about TCP in wired networks and not wireless networks. Okay, so in wired networks, any packet loss is mainly due to congestion. And the other way of finding out about congestion is when we receive 3 duplicate acknowledgements signaling the loss of a packet. Congestion control policies, we have 3. We have the slow start mechanism, we have congestion avoidance, and we have fast recovery. So how does the congestion window work? We have, initially the congestion window will be set to 1. Okay, so at the client side, when we begin the transmission, we send 1 packet and we wait for the acknowledgement. If we receive the acknowledgement successfully, we now increase the congestion window to 2 packets and we wait for the acknowledgements. Successful, we increase it by 4. So this is 1, 2, 1, 2, 4, 8, 16, 32, 64, until we reach the threshold. So as you can see here, the increase for every successful acknowledgement that we get, we are increasing the congestion window by double the size. Okay, so this is called an exponential increase. Okay, it's called an exponential increase. Why are we doing this? Because we are starting from a speed of 0. Okay, and then we build it 1, 2, 4. If we were to build it 1, 2, 3, 4, 5 in this way, it will take a long time for us to reach the speed we desire, and we will end up wasting a lot of time. So to avoid that, initially we have a phase called exponential increase. So if we were to draw a diagram depicting this, we would have something of this type. So we have, let's draw the graph. Now, so initially the size of the window is 1, okay? So we're sending 1 packet. When we receive a successful acknowledgement, we increase it to 2 packets. When we get a successful acknowledgement, we increase it to 4 packets. Again, successful, increase it to 8. And then 16. Okay? So as you can see, the speed is increasing exponentially. Okay? This is the exponential increase. And this phase is called the slow start phase. Okay? The slow start phase. So for how long does this carry on? This carries on until we reach a certain point called the slow start threshold. Okay, slow start threshold. At this point, after we reach this point, now, if we were to continue increasing it exponentially, we will definitely encounter congestion. So to avoid that, after we hit the slow start threshold, for every successful acknowledgement, we increase the window size by 1 only. Okay, so the window size will increase in this way, steady increase. And this is called the additive increase. Additive increase. Because for every successful acknowledgement, we are only increasing the window by 1 packet. So for how long does this go? This goes on as long as we do not receive a packet loss. If there is a timeout, indicates a loss in packet. A loss in packet indicates congestion. So in normal TCP, in basic TCP, the window size is brought down all the way to 1. And this threshold is reduced to half. Okay, it can reduce to half. Now, based on what type of TCP we are using, there will be a difference in how the threshold is reduced. So in this case, we would say the threshold is brought down to 8. And then we go on increasing again in this way. Okay, so this is how we deal with congestion in TCP. Why are we doing this? Because the assumption is that in this scenario, as we have a congestion at this router, the best way to resolve this congestion is to reduce the speed of these 2 routers. If these routers reduce their speed of transmitting packets, automatically we will have a reduction in congestion at this router. And so this is what TCP aims to do. Whenever it detects packet loss, it will bring down its throughput so that any congestion that is there in the network will automatically get cleared. Every client does this in standard TCP. So this is slow start exponential increase. And this is the congestion avoidance phase, which is additive increase. So this phase is called congestion avoidance. So we have slow start, congestion avoidance, and we have fast recovery. Now we will look at some flavors of TCP, some different versions of TCP. We have Tahoe TCP and we have Reno TCP. Tahoe will make use of slow start and congestion avoidance only, whereas Reno makes use of fast recovery as well. So let's look at how this takes place. Now we are looking at Tahoe TCP. So we start at 1, the congestion window, and we move on 1, 2, 4, 8. At 8, at this time, if you see the original slow start threshold has been set to 16. But before we reach 16, we have encountered a timeout, which means we have congestion in the network. As soon as it detects a timeout, the client will bring down its throughput back to 1, the congestion window back to 1. And the threshold, the slow start threshold, the point that we encountered the timeout, we take half the value of it and we make that as our slow start threshold. So as you can see, all the way from 16, the slow start threshold has reduced to 4 only. So again, we have 1, 2, 4, and then we go into additive increase, one at a time. At this point, we have encountered 3 duplicate acknowledgements. 3 duplicate acknowledgements also indicate a packet loss. So once again, we bring down the speed back to 1. This was the point where we encountered it at point 12. We bring down the threshold to half of it, which is 6. And the process continues again. So if you see here, these lines will indicate this is the slow start phase. This again is a slow start phase. This is congestion avoidance. Slow start, congestion avoidance. All right. So this is how Tahoe TCP works. The next we have is Reno TCP that also makes use of fast recovery. In Reno TCP, you started at 1, 2, 4, 8. A similar scenario. So the original threshold was at 16, but at 8 we experienced a timeout. Because it's a timeout, we have not received the acknowledgement even after waiting for the retransmission timeout period. So we have waited for the acknowledgement, we didn't receive one, so we bring down the congestion window to 1. We halve the size of the slow start threshold to 4, and we go 1, 2, 4, and additive increase. Now at this point, we have 3 duplicate acknowledgements. What do we mean by 3 duplicate acknowledgements? If you remember, it means that we have sent the packet and we have started the timer. Okay, now this is where the timer should finish technically. Okay, so until this timer finishes, we will not resend the packet. In the meantime, we know that we have received 3 duplicate. So this was lost. So we have received 3 duplicate acknowledgements. At this point, we have finished the 3 duplicate acknowledgements. So our timer, there is still not a timeout. Okay, there's still a chance that we could still receive the acknowledgement. So because we still have not lost hope, Reno TCP does not go down to slow start. What it will do is, now at this point, this is the point where we experience the 3 duplicate acknowledgements. So we bring down the threshold to half of that value, which is 6. But we don't come back to 6 or any other place. We do slow start threshold plus 3. So we will do 6 plus 3, 9. So this is the point where we come down to. And in here, we go ahead and do exponential increase again. Okay, so we are doing here 9, 10, 12. At this point, we receive the acknowledgement. So before this timer expires, somewhere here, we receive the acknowledgement for this, the acknowledgement that was not there, we have received it, which means everything is fine. Now, if we were to continue increasing exponentially, we will again face congestion, definitely. So to avoid that, we bring down our speed to slow start threshold, which is 6, and we carry on with additive increase, congestion avoidance. So this phase is fast recovery. All right, so this phase is fast recovery, and this is congestion avoidance. So we carry on where we left off. So this is the functioning of Reno TCP. And with this, we come to an end of our chapter, Transport Layer Protocols.